Hello friends. Today we are going to discuss questions, and these questions are from year 2012. So in the first question, it is said that a cylindrical cavity of diameter A exists inside a cylinder of diameter 2A as shown in the figure. Both cylinder and the cavity are infinitely long. A uniform current density J flows through the length. If the magnitude of the magnetic field at the point P is given as NAJ mu naught upon 12, then the value of N is. So we are given this figure, and there is a cylinder, and we are having a cavity, and this cavity is having you can say diameter of A, and the entire cylinder is having a diameter of 2A, and we have to find out the magnitude of magnetic field at this point P, which is, you can say, at the end of the diameter, opposite end of the diameter. So first of all, we are going to find out the magnetic field at point P because of entire cylinder. Then we are going to find out separately the magnetic field of the cavity, and then we are going to do the algebraic sum for that. Okay. So we start from the complete magnetic field of a complete cylinder, and for that you can say due to current in the complete cylinder, the magnetic field at P let us suppose we write that B1, then this B1 will be equal to mu naught upon 4 pi, and here we have 2I and divided by A, and here current is not given to us but given as current density, so therefore we can modify the current equation and write it mu naught 4 pi 2 upon A, and this comes as pi r square multiply the current density, that is J, and this gives us that our B1 will be equal to mu naught A current density J and divided by 2, and this current density J, or we can say current I, is for the entire cylinder. So we are going to find out in proportion how much current is actually flowing through the cavity. We say current through the cylindrical cavity of radius A by 2 let us suppose it is given as I prime, and then this I prime will be equal to total current divided by total area multiplied by the area of the cavity, that is pi A by 2 whole square, and from here we get that I prime is equal to I upon 4. So this is the current that will be flowing through the cylindrical cavity if it was present there. Now we find out that the magnetic field because of this current I prime. You can say due to current in cylindrical cavity, the magnetic field at P let us call that B2. So B2 will be equal to, this will be our mu naught 4 pi, and this we have I upon 4 divided by A plus A by 2. So this gives us, one second, I think 2I, yeah, 2 is missing from here, 2I, okay, it should be 2I prime, and this gives us mu naught upon 4 pi, and this will be equal to our 2I, and we have here 4, and this will be coming as 3A by 2. So which gives us that our magnetic field will be equal to mu naught 4 pi, and we can convert this current I into now current density, this giving us pi a square multiplied by J and divided by 6A, and this will be 2. So we get this as mu naught A J divided by 12. So now we find out the net magnetic field at P. Net magnetic field at P, let us suppose that is given as B, so that will equal to B1 minus B2. We substitute the respective formulas for B1 and B2. We get B is equal to mu naught A J upon 2 minus mu naught A J upon 12, and this comes as 5 mu naught A J divided by 12. But we are given that the net magnetic field is equal to NAJ mu naught upon 12. We are given this as N mu naught A J upon 12. So therefore 1:1 comparison gives us that value of N is equal to 5. So this completes the first question. Now we come to the next question. It says that consider, it was also asked in the 2012, consider motion of a positive point charge in a region where there are a simultaneous uniform electric and magnetic field. Direction of electric and magnetic field is given as E is equal to E naught J unit vector and B is equal to B naught J unit vector. At time t is equal to 0, this charge has a velocity v in the xy plane, making an angle theta with the x-axis. Which of the following options is or are correct at t is equal to greater than 0? So we are given that we have a electric field which is given as E naught J unit vector. We have a magnetic field which is given as B naught J unit vector, and it means both are along positive y axis. So you can positive y axis. Secondly, we are given that at t equal to 0, velocity, that is our v, is in xy plane. XY plane, making an angle theta with x-axis. Making angle theta with our x-axis. So we can draw an approximate figure for that. So this is our x-axis and we have y-axis, and both electric and magnetic field are, you can say, in this direction. So this is electric field as well as magnetic field, and the velocity v is in xy plane, and this is making angle of theta with positive x-axis. So if both electric field and magnetic field are present, then we can say the force acting on the point charge will be equal to QE plus V cross P. So we can say that forces acting on the charge and that force is our F. So F will be equal to Q. Q is the positive charge, so that will be E plus V cross B. And so this V we can divide into two components. We are going to have V cos of theta, and another one will be V sine of theta. So that these two components of the velocity vector. So therefore we can say that velocity v is at an angle theta to x-axis. Therefore, toward x-axis the component will be v cos of theta, and toward y-axis the component will be v sine of theta. And the z component is obviously 0 because it is in xy plane. Now let us find out the, you can say, magnetic force by substituting all these, you can say, formula equations for electric field, magnetic field as well as velocity. And we can also write that our velocity can be written as Vxi plus Vyj plus Vzk, and Vz is our 0 because, let me write it here, our Vz is equal to 0 because of xy plane. So we can write this as our Vxi plus Vyj. Now we need to find out our cross product of velocity and magnetic field. So you can say V cross B will be equal to Vxi Vyj cross, and B is having only J component. Therefore, we get this as Vx B naught K unit vector. So we can write that our magnetic force Fb, which is our Q V cross B we just found out, this will be coming as Q Vx B naught K unit vector, and our electric force that is of Fe will be equal to charge multiplied by electric and J unit vector. Therefore, total force total force, that is called Ft, will be equal to Q E naught J plus Q Vx B naught K. So this is the total force. And let's take the options one by one and try to sort out the which one is the correct one. In option 1, we are given that our theta is equal to 0. Yeah, theta is equal to 0. So we have to find out whether charge moves in circular path in the xy plane. So if theta is equal to 0, let's find out the magnetic force, that our Fb will be equal to Q, and that will be our Vx is our V cos of theta. So V cos of theta is, let me write it here. So Vx is equal to V cos of theta. Theta is 0, so cos 0 is 1. So this gives us V. Therefore, the magnetic force will be equal to QV B naught K into vector, and the electric force is independent of angle theta. So we get our electric force is equal to Q E naught J unit vector. Now let us make analysis of the motion, in which direction it is going to move or behave. So we have motion analysis. First of all, let us say about x component. In x component, there is no force in x direction because magnetic force is in K, electric force is J. Okay, so we can say no force in x direction. Now we come to the y component. And the y component, only our electric force is along the y component. Okay. Only electric force. Therefore, we can say acceleration in y component will be equal to the force divided by the mass. And we have a z component. And z component, we have only magnetic force. So we can say our acceleration in z component will be equal to QV B naught divided by m. Okay. So there are two motions. One motion is along y because of the electric force, and another is because of the magnetic force. And initially it states that the velocity is only in x direction. So magnetic force causes the in circular motion, okay, and the electric force causes a linear acceleration in y direction. So simultaneously there will be two motions, you can say, taking place. One will be in circular and another will be linear. So because of this, it will be a helical motion along the you can say involving the z axis. You can say that Fp, that is a magnetic force, results in circular motion, whereas electric force results in linear motion. So we can say that the resultant motion is helical. So therefore option A is incorrect. Option A is incorrect. Now we come to the option B, and in option B it states that once again theta is equal to 0. The charge undergoes a helical motion with a constant pitch along y-axis. And here it mentions that constant pitch, but because of the force of electric, that motion will be accelerated motion, so the pitch cannot be constant. No doubt it will be helical motion, but the pitch cannot be constant. So we have option B, and it says that helical motion with constant pitch along y-axis. Okay, and I forgot to mention that in part A the resultant will be helical and involves z-axis and involves z-axis. So therefore no doubt the motion will be helical, but because of, you can say, the electric force causes a results in constant acceleration. Therefore pitch is not constant. Pitch is not constant. So it means option B is not option B is incorrect. Option B is incorrect. Now we come to the option C, and option C said that theta is our 10 degree. So these both are incorrect. And 10 degree, the charge undergoes a helical motion with its pitch increasing with time along y-axis. So we have option C. And here theta is given as 10 degree. Therefore we can write our velocity v will be equal to v cos of 10 I plus v sine of 10 j, and our magnetic force Fp will be equal to q v cos of 10 b naught k, and we have our electric field is equal to q e naught j. Now let us make analysis of motion. Motion analysis. Let us First is our x component. And x component, the initial velocity is v cos of 10 and yeah, so this has two components. One is long here x component and another one is long j component. So we can say that the initial velocity, that is our v cos of 10 times I, is affected by the magnetic force. Affected by magnetic force, because magnetic force is along j axis, causing circular motion. Causing circular motion. We come to y component. And the velocity also have a y component, that is v sine of theta and j unit vector. You can say initial velocity v sine of 10 j is affected by affected and accelerated by electric force. And finally we have our z component. And z component, we have our magnetic field, magnetic force, and that magnetic force is our, it is given as, it is having a z component. Okay. So we can say that due to magnetic force, the charge will have a one second, I think I made a mistake here. Initial velocity vi, yeah, magnetic force is perpendicular, and here velocity is in this direction and magnetic force in this direction. Yeah, this is correct one. So this is our magnetic field and this is our velocity. And due to Fp, the charge will have a circular component in xz plane. Will have circular component in xz plane. So it means all, we can draw a resulting motion from there. So we can say resulting motion, and we are going to have a helical motion because of the circular motion and the linear acceleration in y direction, and the pitch will be determined by the component in y velocity. Okay. So it means y velocity is continuously going to increase and the pitch is also going to increase. Okay. So the option number C that is given to us, yeah, the pitch is increasing. So this option is our correct one. So you can say the resulting motion the charge will have a helical motion and helical motion because of the circular component in xz plane and linear acceleration in y direction and linear acceleration in y direction. So it is a linear accelerated motion. So because of this, the pitch will increase in time. So this will be resulting in increasing in pitch. Therefore, option C is correct. Option C is correct. And option D, it is given that theta is 90 degree. Option D, we are given that theta is 90 degree. Therefore, the velocity component, that is our initial velocity, V will be our only j unit vector, and our magnetic force, that is Fp, will be equal to, we have V cos of 90. Okay, so we can write this as Q V cos of 90 times B naught K unit vector. Cos 90 is 0, so this will be 0, and electric field doesn't have anything dependent upon the theta, so I can say my electric force will be same, that is Q E naught J unit vector. Now the initial velocity is along J, and the only force that will be acting on it is because of the electric force. Magnetic force will be equal to 0. Okay. So it means that only electric force acts causing acceleration in y direction. Causing acceleration in y direction. So it means the charge will have a linear accelerated motion in y direction. We can say linear accelerated motion in y direction. And option D is, I think, it is given same. Yeah, linear but accelerated motion in y direction, so option D is also correct. Option D is correct. Next question. In this case, we are given an infinitely long hollow conducting cylinder with inner radius r by 2 and outer radius r carries a uniform current density along its length. The magnitude of magnetic field as a function of radial distance r from the axis is best represented by. So in this case, we are given a hollow cylinder. So from the top view, we can draw the approximate figure. So it is going to have inner radius, and that radius is our r by 2, and we have outer also because it's a hollow, and this radius is given as capital R. So therefore, it is also given that it has a uniform current density throughout the conducting region, and the current density, that is our J, it will be our line for, you can say, we can write it, current density J will be for our greater than R by 2 but less than R. So this will be for our current density J. And we have to find out, in case, let us assume a x which is a variable and it moves right from the center of the cylinder and towards outward in this direction. This is our x. So we can define this x for three parts. First, the x will be less than r by 2, that is the point x is right inside the cylinder. Second, it is greater than r by 2 but less than r, so it will be inside this hollow part, in the cylindrical part. And then last will be x greater than r, that is it is outside the, you can say, entire cylinder or conductor. Okay. So we say, considering x as a variable where the magnetic field is given as, so in the first, if x is less than r by 2, so it means we are inside the cavity. Second, if our x is greater than r by 2 but less than r, we are within the conductor. And finally, we have our x is greater than r, that is outside the conductor. And we can use Ampere's law in order to find, or in order to solve this. We can say, by Ampere's law, for a closed surface, our B dot dl will be equal to mu naught times current, and this current is enclosed current within this closed surface. You can say enclosed. And for this x variable, we can further write it as that B times 2 pi x will be equal to mu naught and I enclosed, and this gives us that the magnetic field is equal to mu naught I, and we have this enclosed divided by x. So we found out the equation of magnetic field with respect to or dependent upon the term x. Now we are going to take all the three values of x which we just mentioned. So now our x is less than r by 2. X is less than r by 2, and under this condition there is no current enclosed. No current enclosed because current flows only in the conductor, because current flows only in region from R by 2 to R. So therefore I enclosed is equal to 0. So this gives us that a magnetic field is equal to 0. So therefore we can just, at least here A is not the correct option, because the current has to be, the magnetic field has to be 0 up till R by 2. So initial graph, this is our R, we have a magnetic field. So initially up till distance R by 2, the magnetic field will be equal to 0. So this is our R by 2 and magnetic field is equal to 0. Now we come to the second part where x is greater than R by 2 but less than R. Now here you can say we are going to find out the current, because now the current only flows inside the conductor. Okay. And we have considered a x, so let us do it for R by 2x. Okay. So we can say that the current enclosed is the current only in the portion from R by 2 to x. And current density is given to us as J. Current density is given as J. Therefore, we can write that area of enclosed current, area of enclosed current, that is equal to pi x square minus the area of the cavity, and this gives us pi, and here comes as x square minus r square divided by 4. So this is the area, and now we can find out the enclosed current. Enclosed current, that is our I enclosed, will be equal to current density multiplied by area. This gives us that I enclosed will be equal to current density, we already know is fixed, and area we just found it is our pi, and we have here x square minus r square by 4. Therefore magnetic field, that is our B, which is our mu naught I enclosed divided by 2 pi x. So this gives us mu naught J upon pi x, and here we have J pi x square r square by 4. Pi cancel with pi, and we get that magnetic field B is equal to mu naught J upon 2x x square minus r square by 4. And now we come to the, we can say, third part, when r is greater than, sorry, x is greater than or equal to r. X is greater than or equal to r. So the total area enclosed. Now in this case, because we have enclosed entire conductor, so the complete current will be enclosed. So we can say now all the current is enclosed. Therefore, first of all, we are going to find the total area, and based on this we find out the total current. So you can say total conducting area is equal to A, we have it is pi r square minus pi r by 2 whole square, and this comes as pi r square 3 by 4. Current, total current, that is of I is equal to J multiplied by A. This comes by J pi, and we have 3 by 4 r square. Now the magnetic field, because this will be current, will be our enclosed current. So magnetic field B, which is our mu naught I enclosed 2 pi x. So this gives us mu naught J upon 2x, pi goes with pi, so we are left with 3 by 4 r square, and this gives us that it is 3 mu naught J r square divided by 8, and we have 1 by x. And here in this case we can clearly see that with the increase in x, the magnetic field increases in a curved manner, okay, and it reaches when x is equal to maximum when x is equal to r. Okay, and say this increases with x in a curved manner, and B is equal to B max when x is equal to r. So for the curved portion, option number B and C, the increase is, you can say, vertical, whereas it has to be a curved manner. So option number D is the our approximate choice for that. And this can be further from the last part also. We can say that our magnetic field B is inversely proportional to x. Okay. So it means that the final graph will be something like this. This is x, and we have magnetic field, and initially it is 0 up till r by 2. Then it makes a curved increase to a maximum value, and that maximum value is at r, and then it is something like decrease. So option D is the correct one. Option D is correct. Now we come to the final question. It was also asked in the year 2012, and it states that a loop carrying current I lies in xy plane as shown in the figure. The unit vector k is coming out of the plane of the paper. The magnetic moment of the current loop is. So we are given this is a current loop. It's basically a combination of the square as well as a semicircle. Okay, so we can just complete the square. So this will be the square, and we have the semicircles then. So magnetic moment, we can break this entire into two parts. One will be consisting of the square and other will be consisting of this four, you can say, semicircles. Okay. And we can just find out their individual magnetic moment and solve them, or we can say add them. So we know that magnetic moment that is m, it is given as I, A, n unit vector, and this unit vector is the normal to the loop. In this case means direction, which is given as k out of the paper. You can say this unit vector, so we can call this as a unit normal to the loop, and that is along k positive. And like I said, we are going to break the loop area into two parts mainly. So you can say breaking loop area, we have central square area A1 A square, and we have second four semicircles, and radius r is equal to a by 2. Therefore we can write area A2 is equal to 4 times half pi r square. So this comes as 4 times half pi, and we have a by 2 whole square. So this gives us that our A2 is equal to pi a square divided by 2. So total area will be equal to A1 plus A2. Total area, that is our A, will be equal to A1 plus A2. This comes as A square plus pi a square by 2. This is our A is equal to A square, we can take as common. This comes 1 plus pi by 2. So magnetic moment, that is m, is equal to I area total, and normal unit vector is k. Now we substitute value of our area, we get moment is equal to I a square, and we have 1 plus pi by 2 k unit vector. So this is our magnetic moment, and the option is our option number B is the correct one. Option B is correct. So these were the questions that was asked in the year 2012. So these complete all the questions. Thank you.